where does it come from? What deeper principle does it arise from? That, to me, is the real puzzle.
Problem we want to solve is an old problem. Where does quantum theory come from? What is the deeper foundation underneath? What is the deeper principle from which quantum theory arises from? What is the property of the universe that enforces quantum theory? Some definition. Whenever I said measurement, what I really mean, and especially how I will represent a measurement. A measurement is an interaction that produces an outcome and transforms the state of the system into a new state. A reasonable question is, well, what is a state? For our purposes, it's enough to say that the state is some object that encodes the probabilities of the outcomes of future measurements. Okay? Might encode much more information, but at least should encode this information. You can characterize a measurement through a set of transformations, each transformations corresponding to each possible outcome of the measurement. Some notation, input state, the state you have before the measurement is raw, the state after the measurement M on the input state raw with outcome X will be denoted this way. And the transformation Mx of the input state raw when M gives the outcome X is what I will call an event. And I will denote this way. And I am interested in the probabilities of events that I will denote this way. The Born rule has a very innocent appearance, but has two parts, and both constitute the Born rule. The first part says that states are represented by unit vectors. The second part says that the probability of an event is computed through these unit vectors this way. You take the dot product of the unit vectors, absolute value, square. Fine. But now the problem is, what property of the wall enforces 1 and 2 together? And for this we need a key concept, which is the concept of ideal measurement. This definition of ideal measurement comes from Julia, and said a measurement is ideal if, first, it gives the same outcome when performed consecutive times. Second, only disturbs measurements that are incompatible. Third, each of its coarse grainings has a realization that satisfies the first and the second point. And in addition, we will assume that two ideal measurements, each of them on a different system, constitute also an ideal measurement for the joint system. What I mean by all these technicalities. So, first of all, what I mean by disturb, only disturbs incompatible measurements. Okay? One measurement, first measurement, disturbs a second measurement if from the outcome statistics of the second measurement we can detect whether the first measurement was performed. If we can, then the first measurement disturbs. If we can for some state maybe, if we cannot for any state, then there's no disturbance. Now the notion of compatibility. Okay? Let's go to the notion of compatibility rather than incompatibility. Two measurements are compatible or jointly measurable when there is a third measurement such that out of this third measurement, we can extract the outcome statistics of the first and second measurement for any initial state. Otherwise, we said that they are incompatible. And finally, the concept of coarse-graining. A certain measurement is a coarse-graining of another measurement if for all outcomes of this M, there is an outcome of this coarse-graining such that for all initial states, these probabilities happen. I would say that all these three concepts are standard concepts, so these are well-known concepts in many. But let's go to the point that somehow I'm putting a lot of emphasis on this concept of ideal measurement. Okay? Why? Why I'm doing that? What is the reason? Well, one reason is the observation that, in a sense, quantum theory is only about ideal measurements. This is kind of surprising in the era of quantum information, but there's a very old 1940 theorem saying that what we call generalized measurements in quantum theory, and we represent by POVMs, can be always seen as projective measurements in a larger Hilbert space. This is Neumark's theorem, is, as you said here, for the 40s, but the point is that it was introduced, to my knowledge, in quantum theory around 1980, probably by Holevo. Initially, actually in Russian, and only until 1982 or something like this, you have an English book making emphasis on this point. And I invite you to examine this that looks like a pure mathematical claim after having seen the transparency of how I create qubit, Q-trees, and Q-quarks. How easy is in the lab to expand the Hilbert space, really, to do that. Okay? Saying otherwise, when you go to the lab these days and you want to implement a POVM, what you do is you do a projective measurement in a larger Hilbert space. This is what you do. Okay? So somehow, that's the message, somehow, for some reason, quantum theory is all around ideal measurements. But people object to this idea in measurements in the sense, well, but most measurements are not ideal. Yeah, well, I'm not assuming that ideal measurements can be implemented with infinite precisions or in a perfectly noiseless way. We only assume that ideal measurements exist as idealizations in the same sense Galileo made idealizations in his experiments. He had friction, but he thought, well, if I would be living somewhere else in the moon, I didn't have friction with the air because there's no atmosphere in the moon, things like this. Okay, so they are idealization. And this is the point. Actually, the assumptions we are making is that the physical theory must at least give the probabilities for the outcomes of ideal measurements. Okay? In fact, the assumption is simply that physical theories are possible. In particular, the assumption that there are similar experiments in different parts of the universe, that they are similar in the sense that they are described by the same laws. They follow the same statistics. This, you may say, is an assumption, and yes, it is. But there's also the assumption that there are independent experiments, which simply means, imagine you have two of these similar experiments in different parts of the universe. You might watch at them as if they would be a single experiment. And therefore, the probabilities of each event of this single experiment were just the probabilities of the corresponding event in one of the little experiments times the probabilities of the corresponding event in the other little experiment. Okay? So think about the implications, because it sounds like strong assumptions, but these are the assumptions we typically do in physics. So now let's move to the second part. This is the hard part. This is the approach, I promise, in which you study theories, general probabilistic theories, theories that assign probabilities to the outcomes of measurements, in particular to the outcomes of ideal measurements, that are more general in principle than quantum theory, or less general, like the case of classical probability theory. Okay? We will be watching them from a new perspective, and this new perspective is the one I would like to introduce now. The graph theoretic approach developed together with Simone Severini and Andreas Pinter. First, we have a definition of event. We need a notion of equivalence between events. Two events are equivalent if they correspond to indistinguishable transformation of the same state. If I do anything I can do, my theory allows me to do, and I cannot distinguish these two events, I will declare them equivalent. But at the end of the day, it's all about the transformations. So I will say that two transformations are equivalent if the events they produce are equivalent for all initial states. The second key notion is exclusivity. Two events are exclusive if there is an ideal measurement with two different outcomes such that one of the events is equivalent to the event corresponding to one of the outcomes of this ideal measurement, and the other event is equivalent to the other event corresponding to the other outcome of the ideal measurement. Two transformations are exclusive if all the events for any initial state they produce are exclusive. Okay? So now we are in a situation in which we have a physical theory or a general probabilistic theory with a set of transformations. We have a notion of equivalence between transformations and a notion of exclusivity between transformations. Okay? So in particular, I can pick some of these transformations and ask me the following question: whether they are equivalent or exclusive. Okay? If they are equivalent, I put them in the same class. If they are exclusive, I do the following. This is a class of equivalent transformations. For instance, red and triangular. You have an initial state, can be old. You made a measurement, and after the measurement, the state you assign is that the system is red and triangular. Okay? Between the initial state and the final state, there has been a transformation. Or another transformation is that system is rectangular and big. Now the question is why I put an edge between these two, and the answer is because these two are exclusive transformations. The reason why red and triangular and rectangular and big are exclusive is because there is an ideal measurement, in this case a measurement of the color, shape, and size, such that for any initial state, the transformation leading to red and triangular and the transformation leading to rectangular and big corresponding to different outcomes. In brief, these two things cannot happen at the same time, are exclusive results. And similarly, you explain all the edges. This is what we will call a graph of exclusivity. And this will be the key object in our approach. But this is a graph of exclusivity for a particular set of transformations. Instead of that, I can come with a theory together with all the possible transformations and draw a pentagon and ask you, okay, now imagine within your theory and using this set of transformations all possible ways you have to organize the transformations such that they produce a pentagon, like this. A key observation is that when I said, well, but are all these graphs possible, feasible? Notice that they are, in any reasonable theory, starting with classical probability theory. Using the sort of trick that is behind this construction, adding properties, classical properties, is easy to make sense of any arbitrary graph you might be interested in. So not only in quantum theory, not only in any non-strange general probabilistic theory, but in particular in classical probability theory, all graphs, all exclusivity graphs are feasible. But we are not interested in graphs for a particular set of transformations. We are interested in all possible ways within a theory of generating these graphs. So the definition, the notion of graph of exclusivity that we will be using is, given a theory, we will call the graph of exclusivity as the one that represents the set of all sets of equivalent classes of transformations produced by ideal measurements such that they have this particular graph as graph of exclusivity. For instance, I give you a pentagon and I ask you to imagine all possible ways in classical physical theory to produce pentagons. And we can talk later, but it's easy to see, for instance, in a Bell scenario, there are plenty of pentagons. In many scenarios are plenty of these ways. So instead of analyzing a scenario by a scenario, the game here will be, okay, let's analyze all possible ways to make a pentagon, all possible ways to make an heptagon within a theory, and compare between different theories. Actually, what we are interested in is in what probabilities are valid within a theory for a given graph. This is what is called a probability assignment for the graph of exclusivity, which is nothing that you assign probabilities to the vertices of the graph. But you have to satisfy at least one condition. If you have two vertices connected by an edge, it's because they are exclusive. They cannot happen at the same time. Therefore, the sum of the probabilities you assigned cannot be larger than one. Okay? That seems like a basic rule. Well, and what is the connection between this key notion of ideal measurement and graph of exclusivity? This is also a theorem by Giulio. That the events produced by ideal measurements satisfy the so-called exclusivity principle. If you have a set of events such that every two events in this set is exclusive, meaning they are pairwise exclusive, then all the events in the set are mutually exclusive. Example first. Imagine a set of three events such that they are pairwise exclusive. A and J are exclusive, J and K are exclusive, A and K are exclusive. This means, so far, simply that the probabilities of A and J, the sum of them, cannot be larger than 1 on one hand, A and K cannot be larger than 1, and J and K cannot be larger than 1. But what this theorem tells you is that if we are talking about probabilities of events produced by ideal measurements, in addition, they should satisfy this condition. The sum of the three cannot be larger than 1. This is not within the standard rules of probability. It's an observation. Nothing in the standard rules of probability leads to the exclusivity principle. Other way of saying, the probabilities of the outcomes of POBMs in quantum theory don't satisfy the exclusivity principle. But of course, the probabilities of the outcomes of ideal measurements or projective measurements in the case of quantum theory do satisfy the exclusivity principle. Okay? And this is the problem. The first problem is, okay, this is a kind of different approach, but is it useful to distinguish between different theories? Okay? So given a theory, you can answer this question: what is the set of valid probability assignments for any graph of exclusivity? You can somehow tell me, for classical probability theory, no matter what the graph is, the set you have, the set of what is valid, what is doable within the theory is this, and the same for other theories. And yes, and the surprise is that, for instance, this is for classical probability theory. It's easy to prove that the set of valid probability assignments for any graph is defined this way. And the funny thing is that in graph theory, people put a name to this set many, many years ago with no relation whatsoever with physics. It's called the stable set polytope of G. It's a polytope. Okay? For any graph, the set of valid probabilities within the theory is a polytope. Okay? For every graph, for each graph, you have a different polytope. The bigger the graph, the bigger the polytope. Okay? And what about quantum theory? Well, for quantum theory, we discovered that the set of valid probability assignments is this thing. I will go into detail later. And the shocking discovery was that in graph theory, some people have named it in connection to a problem, again, totally unrelated to physics. And it's called the theta body of the graph. And now the question is, and well, what about more general theories? What is the only restriction we have? The only restriction we have is the exclusivity principle, because we are talking about the outcomes of ideal measurements, and they should satisfy the exclusivity principle. So I said, okay, what is if you just apply the exclusivity principle watching a graph, what is the largest set you can? Well, we work on that, and again, in graph theory, people had a name for that as well. Okay? It's, again, a polytope, but it's called the clique-constrained stable polytope. Okay? Be aware that more general probabilistic theories here means that we apply the exclusivity principle, that's it. But I have to be honest, and actually what is really said is we apply the exclusivity principle just watching the graph, not thinking that the graph can be embedded in the larger graph or is part of a universe. So just watching, you apply the exclusivity principle to the pentagon, say, look, this. But the pentagon represents experiments in the universe, experiments that can be always enlarged. So if you are serious, you have to start thinking in all the ways the exclusivity principle might make an effect. Okay? But let's go back to the quantum set. Well, the quantum set contains the Bohr's rule. Amazingly, okay, I choose on purpose a notation that is sort of a standard, is direct notations in quantum physics. Of course, in the books of graph theory, you don't find this notation, but trust me, they said exactly this. The set of valid probability assignments are probabilities for each vertex such that each of them is computed through a vector, which is, well, we'll see later, dot product another vector, square, absolute square. And each of the vectors is a unit vector. And whenever the transformation leads to exclusive events, the probabilities, the dot product is 0. But now, obviously, you end the paper saying, okay, good, this is a very nice perspective. But it doesn't change the world in the sense you still have the same problems as before. You want to know why. There's a different perspective, but the questions are the same. In particular here is, what is the physical principle that out of the all possible theories singles out this theta body or quantum set for any graph of exclusivity? And now, actually, there's another problem. Are we really sure that the one we wrote is the largest set of valid probability assignment that is not logically inconsistent? Are we really sure that this set we wrote is not itself logically inconsistent? And if you work harder, you notice, no, actually, there's some inconsistency, and the best you can do is something else. So the question is, what is the largest set of valid probability assignments that is not inconsistent, in particular, that satisfy the exclusivity principle in every situation? Hopefully, this in every situation will become clear in a minute. Now we'll talk about all results. Okay, that were nice at that time. And the movie I promised FQXI to produce initially had this nice title: A Tale of Two Observers Observed by a Third Observer. Hopefully you will understand why. Well, one reason why is because the title matches with the call of the FQXI, but there's a deeper reason. For instance, this is an old problem in quantum logic, and not only in quantum logic. I give you a pentagon of exclusivity. Why cannot have probability 1/2 for this event, 1/2 for this event, 1/2 for this event? Is it violating the exclusivity principle? At first sight, no, because the sum of 1/2 and 1/2 is 1, so happy. In 1978, Ron Wright took it as an example of the existence of superquantum logics. Finally, this is exactly inside the famous Popescu-Roerlich non-local boxes. I can prove it in a minute. But it's exactly the same. They create an artifact which has exactly the same probabilities. It produces several pentagons, 8 to be precise, each of them having this assignment of probabilities. Is it a valid probability assignment? Or is it just as they sell it, the idea? An example that there are something else beyond quantum theory. Actually, this is inside the set we constructed at the end with Andreas and Simone. This is a more general probabilistic theory. This is an example of something that, careful, something that is not quantum. The question is, can you do this with quantum theory and projective measurements? And the answer is no, you cannot do. So the question is it valid? And is it not valid? Why not? So again, the same questions in a different language. Well, this is the answer. Imagine you are doing somewhere in the universe one experiment such that it produces events whose graph of exclusivity is a pentagon. The assumption is that you can do physics, that physical theories are possible, that experiments with following the same rules exist somewhere else in the universe. So imagine one of these experiments somewhere else in the universe, but now you are not here or here, you are there. You are really watching those things at the same time. So for you, these two experiments are just one experiment. So for you, instead of this small graph of exclusivity and this small graph of exclusivity, there will be, with the same events and the same events, another graph of exclusivity. This is the graph of exclusivity of your 25 events. And as always in this business, you discovered that it has a name in graph theory. It's the graph that is obtained doing the OR product of the graphs. Okay? So we have three descriptions: local description, location number one, local description, location number two. But you might think both experiments as one. And what about the probability assignments that are possible? Well, here we don't know. We call P1, P2, P3, P4, P5, whatever. But we are assuming that the experiment in the other place of the universe is similar. So it always gives you the same probabilities as there, P1, P2, P3, P4, P5. We are also assuming that they are independent experiments, meaning that when you describe them, the probability of the joint event red and yellow is nothing but the probability of red times the probability of yellow. So this is the assignment of probabilities you would make out of these two ideas. And now is when the thing becomes interesting. Because out of this chaos, or beauty, depending on, you notice this. Look, these particular 5 events are pairwise exclusive. Therefore, they should satisfy the exclusivity principle. The sum of their probabilities cannot be larger than 1. But not only that. Leave it there. Oh, another 5 like this. Another 5 like this. Another 5. And another 5. And what if you sum all these inequalities? Well, this is this. Isn't this a reason why you cannot have probability 1/2? Remember that the square root of 5 is 2.36. If you assign probability 1/2, you have 2.5. You are violating the principle. So either your measurement producing these statistics is not an ideal measurement, is not repeatable and minimally disturbing, or if it is, what you are offering me is simply inconsistent. No ideal measurements can produce the behavior of non-local boxes. Non-ideal measurements can produce the behavior of the so-called right pentagon. Good. But what about quantum theory? Can quantum theory give you the square root of 5? Yes, it does. It's exactly the maximum violation of a famous inequality in quantum theory called the Klyashko inequality. So notice that for classical probability theory, the maximum is a 2. The moment you violate that, you are in presence of what we call contextuality for ideal measurements. Fine. And then a reasonable question is, Well, contextuality, but you can be contextual in infinitely many ways. What is the contextuality of quantum mechanics? And for this particular example, is the square root of 5. What a nice coincidence, right? That is exactly the maximum logically possible. Good, but I have to be honest. And the pentagon is a very special graph. One reason is the following. For this, you need a notion of a complement of a graph. I give you a graph, for instance, the heptagon. The complement of a graph, which is a node this way, is the graph with the same vertices, such that two distinct vertices of the complement are adjacent if and only if they are not adjacent in the original graph. So the complement of the heptagon is this. And the complement of the pentagon is the pentagram, which is isomorphic to the pentagon. So the pentagon has this special property that is equal to its complement. And this is what is behind the fact that when you do the OR product, you have what we call the complete graph, and you apply the exclusivity principle, and it's very productive. So let's focus a little bit on graphs with this beautiful property. And now I will present briefly a result which is not well known, but I think is really important. I will explain why. It's just about self-complementary graphs, like the pentagon. Okay? Not necessarily that symmetric, vertex transitive, not necessarily, just self-complementary graphs. And is this? If the graph is self-complementary, the exclusivity principle, together with the assumption that we can do physics, exclude any set of probability assignments strictly larger than the theta body of the graph. The proof is rather simple. Suppose an assignment, which is not in this theta body. Well, there is then always an assignment in the theta body of the complement such you are violating the exclusivity principle. But, well, there's no one and the complement. Both are the same. Both are isomorphic. Therefore, after permuting the entries given by this isomorphism, this assignment of the complements becomes an element of the theta body of the original, and then this simply said, no, you are violating the exclusivity principle. It's a kind of simple thing, but it's the only example I know at that time of a simple principle producing not a point, but the whole convex set of quantum. I don't know whether you are familiar with this discussion of trying to identify fundamental principles singling out quantum theory, but typically when you are lucky, you find one principle that explains you why the maximum violation of a given Bell inequality is this. But then you ask what happened with the rest of the possibilities, okay? And all of them fail to explain the rest of the possibilities. So yes, this is a non-standard approach, but this particular result was the first time a principle singled out a non-trivial convex quantum set. The new results. And now this is a tale of two observers observed by a third observer, but each of these two observers is observing four observers. Easy to remember. Okay? All I present here is, let's say, old stuff. This is the new results. And the new results is simply that for every graph of exclusivity, the exclusivity principle, together with the assumption that physical theories are possible, single out a quantum set. Not just for self-complementary graph, but for any graph. And this is the technical proof, and it's based on the following construction. Take your favorite mysterious graph. In my case, the heptagon. I've been devote basically 10 years to understand why the probability assignments quantum mechanics does to the vertices of the heptagon are the ones that they are. And this is the answer. So that's why I choose this. Well, remember, our assumption is that there are plenty of experiments in the universe represented by heptagons, and many of them follows exactly the same rules, correspond to exactly the same situations. Okay? So now consider another portion of the universe in which somebody is doing some of them. Now remember that we are assuming that all graphs are possible, are feasible. Okay? So not only the heptagon, but any other graph is somewhere in the universe. And you may have several copies of them. So this is the complement of the heptagon. There are a third part of the universe in which somebody is doing an experiment, represented who's producing events, whose graph of exclusivity is the complement of the heptagon. And another copy here. Okay? Now, in order to be absolutely honest, because we are in the film, I cannot anticipate at this stage what is the physical interpretation of the next step. So I will just explain the next step, and after I prove something, I will hopefully be able to explain you what is the physical meaning of the whole construction. The next step is you take all the vertices of the first graph and you join them with all the vertices of the second. You do the same between the second and the third. And then you do the same between the third and the fourth. Now everything's clear, right? No, it's not. What is special about this construction? Amazingly, there are two things that are special. One is quite obvious, the other is not that obvious. First of all, as always, no matter how you invent, somebody else in graph theory found it long ago and invented a name for that. So this operation we just made has a name in graph theory. It's called generalized composition. You start with a calligraphic graph, which in our case is this simple graph. Okay. And then you define this graph, calligraphic of a number of graphs equal to the number of vertices of the calligraphic graph. In our case, we put G1, G2, G3, G4 as the heptagon, anti-heptagon, anti-heptagon, anti-heptagon. And then the operation does exactly what we did. Okay? But this is not vital information. What is vital information is this construction that we call H of G has this beautiful property. No matter which is the initial graph G, after doing this construction, the result is a graph which is equal to its complement. If you don't see it, think about the construction as follows. You have the heptagon here, anti-heptagon here, anti-heptagon here, heptagon here. Now an edge represents all the vertices of this graph are connected to all the vertices of this. Now do the complement of that. Okay, the complement is simply that. Right. And now it's easy to notice that both are isomorphic. And what's the meaning of that? Well, we have this previous result I mentioned that the quantum set corresponding to this big graph, the E principle explains it. For self-complementary graph, the E principle singles out the quantum set. So the E principle tells you what is the biggest set of probability assignments you can make to the whole thing. Now the big issue is to relate what is valid for the whole thing, what the most crazy thing you can do for your target graph, which is here. And then is where the other second property of this construction is important. This construction has also the property that no matter how it's G, when you have the final chaotic graph, the only induced subgraphs, an induced subgraph is a subgraph that you keep some vertices and the corresponding edges, and nothing but that. So you have, for instance, in the graph we have before, you have zillions of induced subgraphs. Zillions means hundreds of thousands. Okay? Well, and imagine we play the game. Okay, how many of them are cycles with a not and higher than 5 number of vertices or their complements? In a minute, why these particular subgraphs are key. Okay? Well, the answer is, okay, the question is easy, right? How many pentagons, induced pentagons you have here? None. How you know it? You'll see in a minute. How many heptagons you have here? 2. How you know? You see. How many anti-heptagons you have here? 2. How you know? And you have any other odd cycle or you have any other complement? No. No. The only induced cycles of length 5, odd cycles of length 5 or larger, are the ones that you may have in the initial graphs. Here, here, and the process of connecting everything here with everything here, everything here, with everything here, everything here, with everything here. In this particular case, not in general, cannot produce more of these things. And why these things, why these graphs are special? Because there is a result already in the paper with Simone and Andrea saying that for any graph not having as induced graphs of cycles with n larger or equal 5 or their complements, the set of valid probability assignments for any theory satisfying the exclusivity principle are identical to the one of classical probability theory. Meaning, okay, whatever you can do it with classical theory. Okay? This means that the only non-classicality in this big graph can be in the small pieces, can come from the small pieces. The process of adding more edges cannot increase, cannot give rise to any strange structure that cannot be explained with classical theory. That is, the set of valid probability assignments for this big graph is nothing but this convex hull. Whatever you have, the set of valid probability assignments for the small graph, 0 in the other, 0 in the other, a convex hull of this, which in particular tells you that knowing what is valid for the big determines what is valid for the target graph. Okay? And we have already proven that what is valid for the big, the craziest thing you can do is the theta body of the big, which implies that what is valid for the target graph cannot be larger than the theta body of the target graph. And for quantum theory, the valid probability assignments for the target graph are the ones of the theta body. And now is when I can explain the physical meaning of the construction, saying that I will obviously give you a particular example, but there's no lack of generality in this particular example. It works as follows. Now imagine one of these experiments in one place of the universe, generating events, E1, blah, blah, blah. I'm not making any assumption. This can be super crazy, not necessarily quantum, in principle. Okay? The same here, the same here, the same here. Everything I can do, everything I do when I start putting additional edges here is equivalent to, now you are there, you are watching the 4 experiments, okay? And in addition, you have 3 coins. Coin A, heads or tails, B, and C. So you throw the 3 coins, and depending on the result, you design events the following way. You throw the 3 coins, look at coin A, get 0. Okay? If 0, there are events in which coin A gives you 0, and you consider the 7 events here. There are events in which coin A gives 1, coin B gives 0, and you consider this. And doing this artificial thing, you generate exactly the graph you have in front of you. And in principle, all the craziness should be here. But the fact that it's self-complementary cuts the overall craziness in a particular way that enforces saying, yeah, but here you cannot be more than quantum. So we had 2 problems. One was, what is the physical principle that singles out the theta body, the quantum set for arbitrary graphs? And the answer is the exclusivity principle, together with the assumption that similar and independent experiments exist. Fine. Is it a physical principle? Is the exclusivity principle a physical principle? Well, remember that we have another question, which is, what is the largest set of valid probability assignments that is not logically inconsistent? And now the result. For every graph of exclusivity, no physical theory that assigns probabilities to the outcomes of ideal measurements can produce probability assignments outside the quantum set. This comes from Euler's theorem that, well, if measurements are ideal, the probabilities of the outcomes should satisfy the exclusivity principle. And you said, well, what is the craziest thing you can do with that? The craziest thing, logically consistent. Well, is indistinguishable from quantum. So, this is the proof. For years, we thought that we would understand quantum theory when we identify the physical principle that singles out quantum theory from the set of more general probabilistic theories. But behind this way of thinking is the assumption that there are logically consistent general probabilistic theories that can produce probability beyond those allowed by quantum theory. All these examples of Popescu and Roglic and Ron Wright and many, many others suggested that quantum theory is something very specific in a sea of many, many other possibility theories. But if we focus on, okay, your theory should assign outcomes, should assign probabilities to the outcomes of ideal measurements. This is not the case. The particular way to look at quantum theory we have described here, so that this is not the case. There's no such a big C. And it shows that there is a crucial message in the specific way nature is contextual. The value is not that nature violates the Bell inequality. The real message is in what is the largest violation nature allows for the Bell inequality. Because this largest violation is the largest that is logically possible. Okay? The sets of probability assignments to the outcomes of ideal measurements for each and every graph of exclusivity are indistinguishable from the ones of a universe, fictitious universe, with no laws, no restriction whatsoever, but logic. From this perspective, quantum theory is the largest and wildest theory. There's nothing wilder. And this is, for me, quite disturbing, as it suggests that the principles singling out quantum theory from GPTs that I've been searching for do not exist. And it suggests that the ontological message of quantum theory is that nature has no laws governing the outcomes of certain, this is what poetry came, slices of the world, experiments. But this is stronger than saying, no. The fundamental message behind quantum theory is that nature has a fundamental randomness. Be careful. This says much more than that. There are basically infinite universes with fundamental randomness. The message is much more specific. Among all these things, the craziest one is our universe. So the message is absence of laws and restrictions. Classical probability theory emerges when, in addition to the three conditions in the definition of ideal measurement, we ask ideal measurements to produce outcomes admitting a joint probability distribution. Thank you.